Hello, class. Okay, so we're going to finish off now with lesson 6 from unit 7. And this just goes over the concept that is called the triple scalar product. Basically, it means you're going to do 3 different operations. So it is a combination of doing the dot and the cross product. So for an example, it'd be saying A dot B cross C. Now, how are we supposed to figure out what order to do this? Because the dot product produces a scalar, we would not be able to do the dot product first, because then we'd be doing a scalar cross a vector. And you can't do the cross product unless you have 2 vectors. So that means in order to get an answer that makes sense, the combination is only going to be meaningful if you do the cross product first. Okay, so these 2 have to be done first. And then you are going to do the dot product with vector A. All right, so let's practice that here. It says, given the vectors u, v, and w, evaluate the triple cross product. So we're doing u dot v cross w. So again, you have to do the cross product first. Okay, so you can set up your work a bit here. So we are basically going to do, I got cut off a bit there. -2 on -6 dot, and then now we're going to get our answer for the cross product. Where are we going to get those numbers from? You're going to do your work at the side that we're used to. Right? Set up ijk, ijk. And remember, you have to go in the right order. So the v vector has to be first. Okay? So 3, -4, 8 repeated. And then the w vector next, 5, -2, 7. Then we're going to cancel out and then do the crisscross. So we're going to get -4 times 7, so -28, minus -2 times 8, so minus -12. Then we have 8 times 5 minus 7 times 3, so 40 minus 21. 3 times -2 plus, 3 times -2 minus 5 times -4, so -6 minus -20. All right, so let's simplify that. So that means our cross product will become, remember, 2 negatives make a positive, so we're going to get -12, 19, and 14. So again, this is a vector that is perpendicular to both v and w. And now we find the dot product with vector u. So remember, the answer we get here is going to be a scalar, because dot products always produce a scalar quantity. All right, so let's go through multiplying. We're going to do -2 times -12, plus 1 times 19, plus -6 times 14. And the answer we get is -41. So I'm sure you're probably wondering, okay, we found this number, but what is the significance of the triple scalar product? And this is what it is. If I ever ask you to find the volume of, and then this is going to be our new shape. I know this looks like a crazy word. It's the parallelepiped. Parallelepiped. So basically, I want you to think of that as this shape here. Basically, think of it as a rectangular prism, but instead of having rectangular faces, it has parallelograms as its faces. Okay, so a 6-face solid where every face is a parallelogram. So if you kind of want to think of it that way. All right, so here's a parallelepiped. So the significance of this the triple scalar product is that the magnitude of this answer, so we see here, we can get a negative or a positive answer, right, from the dot product. If we just look at its magnitude, it actually turns out to be the volume of this shape, okay? And here's why. So if we look at this shape at the bottom, so remember, we always start with the cross product, so u cross v. We know that the magnitude of u cross v from our other lesson is the area of the parallelogram that it creates. Okay, so we always know that part, so let's kind of highlight that there. Okay, so the area of the parallelogram is always given by the magnitude of the cross product of u and v. So we know that the volume formula is always area of the base times the height of the 3D shape. So we basically have the area of the base, right? So the area of this parallelogram is the area of the base of the entire parallelepiped. So then what are we going to do to find h, right? H is the actual height. So we can find this, if you notice, the height is the vertical component of vector w, right? So this is the horizontal component, this is its vertical component. So if I had given you vector w, and I had asked you for its vertical component, in this way here at least, notice that, and you're probably wondering, well, why aren't we using sine? Because sine is always the vertical component. In this case here, please note that alpha is given up here. Okay, so often you are going to be perhaps given this alpha. So alpha is the upper angle. It is not the theta down here. Okay, so we see that theta is usually here. Okay, but since we're focusing on alpha, okay, so kind of just highlight that. That's why if you're wondering why are we doing cos theta, or why are we doing cos alpha, not sine alpha, and that's because the vertical component of this would be magnitude of w sine theta. However, we are using a different reference angle. So we are using reference angle alpha in this diagram, which means that if we want to find cos, that would be adjacent over hypotenuse. Okay, so that's just the little change there. All right, so how is this helpful? So we were able to find an expression for height, and we were able to find an expression for area of the base. So volume is area of base times height. So we know area of the base is the magnitude of the cross product of u and v. And then we know the height is magnitude w vector cos alpha. And what do you know? This is the same thing as the triple scalar product. So this answer is equivalent to taking u cross v and dotting it with w. Okay, because I want you to think of it kind of still like projection a little bit. So now be careful here. Like I said, we can get a negative answer, and then that wouldn't make sense for volume. So because the dot product, when we do it all together, the triple scalar product can then sometimes give a negative. So that's why we put the magnitude symbols around it. Okay, so we can come back here and say, okay, just in case this is negative, that wouldn't make sense. So we go back and we put our magnitude symbols there to ensure that we only get a positive. And then it makes sense for volume. And remember to put your answer in units cubed. All right, so if we turn over, so again, anytime that I ask you to find the volume of a parallelepiped defined by 3 vectors, okay, you can go ahead and do the triple scalar product. And again, whatever order they're given in, you can just do it that way. No matter what kind of arrangement you do, it will work out. But usually we kind of give it to you as U, V, and W. Or it can be A, B, C, but it would still follow the same pattern. So the W here, and then the U cross V. All right, so we're going to do the magnitude of this. So let's do our side work for our cross product. Okay, so let's set that up here, IJK, IJK. All right, so notice here we're going to cross these two, okay? So we're going to get 8, negative 3, 4 repeated. And then V has to be second, negative 2, 9, 1 repeated. All right, then we cancel out the last 2 examples, or the last 2 columns. And then we start doing the crisscross. So negative 3 times 1 minus 9 times 4. So negative 3 minus 36. 4 times negative 2 minus 1 times 8. So that's negative 8 times, negative 8 minus 8. And then 8 times 9 minus negative 2 times negative 3. So that will be 72 minus 6. Okay. So I've plugged in vector W. This is the cross product, and again, you're maintaining the magnitude symbols all the way down. All right, so our cross product will simplify to negative 39, negative 16, and 66. So remember, guys, the magnitude of this is the area of the parallelogram, which is the base of the parallelepiped. Okay, and then when we do the dot product here, we're basically doing area of base times height, which is kind of cool. All right, so let's do our dot product. So 0 times negative 39 plus negative 4 times negative 16 plus negative 7 times 66. And you will see that that gives us, sorry, make that the 3 got cut off. That gives us negative 398. Again, this is where that absolute value is coming into play. So we know that this number represents the volume of a parallelepiped, right, with these as its base vectors, okay, and this is kind of the other slant of its one of its faces, and we get 398 units cubed. So you're going to say, therefore, the volume of the parallelepiped is 398 units cubed. Okay, and that is the significance of the triple scalar product. That finishes off Unit 7. I hope everyone kind of enjoyed this last part here, and please let me know if you have any questions. Good luck with your homework.